Bismillahirrahmanirrahim. Assalamu alaikum. So in this lecture we will be talking about Ito lemma slightly generalized, or we will be talking about the form of Ito lemma which is slight generalized. In the previous sessions we discussed that if we have a function which is only depending on Brownian motion, or maybe f of b sub t, then we had seen that its differential is given by this formula, but now we will generalize it a little bit. So now we consider our function is not only depending on this Brownian, but also it is depending on time explicitly. So it's like it's depending on time as well as Brownian motion. Say it's b sub t. Examples of such functions include, let's say we have a function t times t comma b sub t to be t times beta sub t square, or maybe we can have a function g of t comma b sub t to be equal to e to the t times sine of b sub t. So such functions are the examples of those functions, are those processes which not only depend on Brownian, but also they depend on time explicitly. So now we will define Ito lemma for such functions. So we will put it into the form of a theorem. So it says that, so the theorem says that let we have a function f which is depending on time as well as Brownian. Sometimes they write f of t comma x, but it's fine, which is a continuous function. Consider a continuous function with partial derivatives which partial derivatives? These two partial derivatives, I mean these three partial derivative: time derivative of f and derivative of f with respect to this Brownian, and also the second derivative of the function with respect to Brownian. So some books write in place of this b as x, so it's fine, like there is not a big deal, because at the end of the day you need to know things in terms of b. So you have a function which is continuous and it has partial derivatives with continuous partial derivatives. So these derivatives are partial derivatives are also continuous. Then we can have the differential. Then the differential of this f can be given by, then the differential of this f of t comma b sub t can be given by partial derivative of f with respect to beta sub t dbs dbt plus partial derivative of f with respect to t at t comma b sub t plus 1/2 second partial derivative of f with respect to beta sub t, of course computed as t comma beta sub t dt. So that's how the differential will look like. So or in short I can write df equal to partial derivative of f with respect to beta dbt plus partial derivative of f with respect to t plus 1/2 second partial derivative of f with respect to b times dt. So this is going to be differential of it, and we can also write this in the form of integral. So in the integral form it will look like this: f of t comma beta sub t equal to f of a comma beta sub a. So it's like integrating uh, from a to t. By the way, it's also fine. Sometimes we write beta sub t, that is beta is a function of t, or sometimes we write beta sub t, beta of t. So that's also fine. There is no any big deal in it. So a to t, the partial derivative of f with respect to beta sub s comma beta sub s dbs plus, I'm writing the terms here, a to t partial derivative of f with respect to s of s comma b sub s plus 1/2 partial derivative of f with respect to this beta or the Brownian, and all of this is integrated with respect to s. So you can write the differential form or also integral form of the slightly version of Ito lemma. Let's do some examples, but in the next session, like in the next video.